Alright, and welcome back everyone. So in the previous part of this video, we went through the analysis of the heat transfer through the copper pipe, but this time with an insulation. So using the electrical circuits analogy, we went through the thermal resistances, we talked about the log mean area, okay? We discussed that, and we discussed the overall rate of heat transfer in terms of overall temperature difference and divided by the net thermal resistance. Okay, so we developed our model. Our model was not really a problem. So now in this part of the video, we're gonna use these values. We're gonna use these values to actually calculate the rate of heat transfer using Excel. Okay, so I have everything labeled and ready to go. So now I'm just gonna start adding my values and my equations. So my temperature at the inside wall of the pipe was 500 Kelvin, and the temperature at the outer wall of the insulation was 298 Kelvin. The conductivity of the pipe, since it's a copper pipe, the value of conductivity that I'm using is equal to, okay, yeah, 395, good. 395, good. All right, the insulation, the thermal conductivity of that. Of course, the thermal conductivity, we want the thermal conductivity of the insulation to be small because that's the idea behind insulation, right? So our inner radius of the pipe, outer radius of the pipe, okay, and finally the R3 is going to be the outer radius of the insulation, 0.05, and the axial length that I'm going to select is going to be 50 meters. Okay, so that's the one that I'm using. Okay, again we have the Excel sheet, so you guys can play around and use whatever values that you find, or whatever values describe your system. Okay, so the log mean area, okay, I have the equation here. I have all the main equations here. So it's just gonna be the I'm gonna start off by writing 2 pi times the axial length. Okay, we're gonna make that an absolute reference. Okay, good. All right, and multiply that by the difference. And for the copper pipe, it's going to be R2 minus R1. So that's the thickness of the copper pipe. And divide that by the natural logarithm of the outer radius divided by the inner radius. Okay. So that gives you the log mean area. That gives you the log mean area of the copper pipe. And to get the log mean area associated with the insulation, I'm just going to drag it here. Beautiful. All right. So just to give it a check. All right, the axial length is the same. L is not changing. Everything else, okay, everything has translated pretty nicely. Very good. So now let's talk about the thermal resistance. Again, I have in cylindrical coordinates, it's just going to be the thickness divided by the conductivity times the log mean area. All right, so we have R2. Let's start off with the thickness. R2 minus R1. Good. Divide that by the conductivity of the copper pipe. And again, there's going to be a division by the log mean area. Okay, I hope you guys are following the order of operations. So that's the thermal resistance of the pipe. Again, we don't expect the thermal resistance of the pipe to be very high because it's made out of copper. Oh, I made a mistake here. My bad. This is supposed to be insulation. I beg your pardon. Okay, now for insulation, let's see how that translates. Okay, so the resistance is when compared to the resistance of the copper pipe, the resistance is much higher, like orders of magnitude higher. And the net resistance is just going to be the summation of these two. Okay, that's our total resistance. Okay, that's our total thermal resistance in our analysis. And let me just check these values before I plug in. Okay, so that's the thickness is correct, divided by the conductivity. That's the right conductivity. And let me just make sure that I'm following everything. Okay, 2 pi L. Good. All right, looks like we're rolling. So now the moment of truth, the rate of heat transfer, Q dot, and that's going to be in watts. And that's just going to be the overall temperature difference, T in minus T out, divided by the net thermal resistance. There you go. So in this case, I can just I can format this. I hope let's get it correct to, yeah, now I can just like play around with the formatting. Okay, I'll just yeah, I'll just let's see. I can go scientific. I mean, now I'm just playing around with the formatting. Let's see, what do I want? I'm good with, okay, I'll just go with 1 decimal point. All right. So correct to 1 decimal point, the rate of heat transfer is 7,116.6. Again, now I can just play around and see if I change the insulation, if I make the insulation, if I use a different material, my rate of heat transfer is expected to go down. So if I am able to select a material that has a lower thermal conductivity, I can reduce the rate of heat transfer. And of course, if the outside temperature of the insulation wall, if I were to decrease that, my overall temperature difference is going to go up. So now I can just play around with this. Okay, the computation is done. Now you can do a parameter sweep. You can find out how varying the thickness. Okay, so for example, if I vary the thickness of the insulation, of course I'm adding more insulation, of course it's gonna go down. But we're gonna spoiler alert, all adding more and more thickness of resistance is not necessarily a good idea. And that's gonna be a segue into one of our next videos, where we're gonna add in external convection into the mix. All right, so just to give you guys a summary, this was our we did our analysis by just deriving our equations. Again, where our assumptions still hold: steady state, constant conductivities, and the fixed temperatures at the boundary conditions. All right, this was our thermal resistance network. Everything looks good, and the overall temperature difference, the overall rate of heat transfer in terms of the overall temperature difference, and the net resistance, the net thermal resistance, good. So for these values, we did the computation in Excel. So overall, a pretty straightforward tutorial, and I hope you guys were able to follow, and I wish you guys best of luck. All right, thank you.